So, well, I'd like to welcome Martin Bendersky from Hunter College at CUNY, who will talk about some remarks on the cohomology of the Vietoris-Rips complex of a hypercube graph.
Thank you, and good morning. This is joint work with Jelena, and in 45 minutes, I'm just going to give a sketch of some of the ideas we've been using to try to understand this mysterious object that seems to be interesting to people who do coding theory, which of course I know nothing about. So to start, Qn is going to be the set of n tuples filled with zeros and ones. And I'll start from that end. There are various ways of thinking of this. Of course, this is the same as using these numbers. This would give the binary expansion of numbers a greater than or equal to 0 and less than or equal to 2 to the n minus 1. But that has nothing to do with the title of the lecture. So that's the other way of thinking of this. These are the vertices of the n-dimensional hypercube. And all of my, those who have attended previously, all of my pictures will be degenerate. I think this is the limit of what I can draw. And this might be beyond my limit as well. So this would be the n equals 2. The numbers between 0 and 3 display as the vertices of the hypercube. Well, once you've got a set of vertices, I mean, we're going to be doing something like that, a Vietoris-Rips complex. The next thing we need is a metric. I'll put it over here. The Hamming distance. For numbers which are in the set Qn is the number of coordinates where A and I and B differ. So for example, the Hamming distance between this coordinate and that coordinate is 1. Between this coordinate and that coordinate is 2. That's the Hamming distance. We could form a graph from this, GNR, where the vertex set is Qn, and the edge is an edge between A and B if the Hamming distance between A and B is less than or equal to R. That R is called the scale. So we have a nice graph. What does one do with the graph? Well, maybe I'll put it over here. The Vietoris-Rips complex, 2 parameters, the n and the R, is the clique complex of GNR. And the problem some people, a few people are interested in is the homology type, cohomology of these things, where they often are wedges of spheres, things of that sort. And I'm not going to get into the discussion of why the hell do the coding theorists give a damn about this. It's an interesting problem in algebraic topology. So some examples. Well, if the Hamming distance is 0, get rid of those edges. Basically, it's the vertex set. If the Hamming distance is 1, you actually get the one skeleton of the hypercube. That's exactly what I drew up there for 2. And by the way, I'll admit my handwriting is awful and I can't spell as well. But if you can't read anything or have any questions, please ask. I have no pride. I'm perfectly happy to write something again. Low for small r, these things are understood. So for example, VRQN2 turns out to be a wedge of 3 spheres. The number of coordinates, the number of wedge factors is completely understood. It's a non-trivial number. And this was done by, as I said, I can't spell, and Henry Adams. QN3 is also well understood. It's a certain number of copies of the 4-sphere. The number of copies are known. And a wedge of 7 spheres. And again, the number of copies are known. So the homotopy type of these things, r equals to 3, is completely understood. And this was done by Feng in 2023. A lot of these calculations are rather recent, actually. Well, I was going to say that for large R, nothing is known. It's completely unknown, except I'm going to mention one case where it is known. If the number of vertices is 1 larger than the scale, this turns out to be a sphere of dimension 2 to the r minus, a triangulation of a sphere of dimension 2 to the r minus 1. Something called a cross polytope, and that'll play some role in the course of these lectures, but that is known. VR nobody knows anything. So what we're going to try to do is give some insight into how these things are, how we understand how to produce homology in these things, try to get some idea about the connectivity of these things and the co-connectivity. One thing which seems to be a feature of the way these people work is with very little evidence, they come up with conjectures. And the conjecture is that I'll use cohomology, what the hell? So the conjecture, at least based on early evidence, was that the cohomology only appears in 2 dimensions. The r plus 1 and 2 to the r minus 1 is completely consistent with the examples. And what's nice about this subject, conjectures like this get shot down very quickly. But they're shot down because they make extensive computer calculations which take a day, and they found some early examples. We're going to extend the list of counterexamples to the connectivity dramatically with some easy graph theory technology. Okay. So how do we want to approach this? And given that it's a workshop in polyhedral products, we want to use some polyhedral product technology. So, and this is not, I think this method has been used quite a bit. So if, in general, forget about the VNR, suppose I have a simplicial complex K contained in M. Now, for the sake of this lecture, because the way the numbers work, I don't want M to be 1 to M. I want M to be the set from 0 to M minus 1. Notice that, where did I have it? The conjecture, for example, there's a 2 to the r minus 1 is going to play a role. And also, the way I label the coordinates, because of the binary expansions, I label it from 0 to n minus 1. So just for convenience. Then we have a theorem that says that we can understand the moment angle complex for k in terms of a torr. I'm not going to be very careful about the indices. Maybe for the moment I will be. V0 to Vn minus 1. I'll use my ground ring of Z for the discussion. There's a torr here, which is giving me the cohomology of the full subcomplex. Oops. I'm not going to worry about the indices for the moment. Ah. Which gives the cohomology of the full subcomplexes. I guess that's called Hochster's theorem or something. In particular, for any k, the suspension of k appears as a direct summand in the torr. And why is this useful? Because within the torr, I could find ways of describing the cohomology in two different ways. I could resolve the k, which would give us the Cazul complex point of view for the underlying cohomology. Or we're going to find that resolving the Stanley-Reisner ring by what's called the Taylor complex gives us some insight into the dual of the cohomology of K. So that's the approach we want to use. So now we'll return. Now I'm going to return to the case of the Vietoris-Rips complex and R. The Stanley-Reisner ring of this thing is easy to describe. Remember, it starts with a graph, so the VRNR, too many R's, is a flag complex. And what are the relations, the non-relations? They're very simple to describe. These are monomials, just the product of two, where the Hamming distance between A and B is greater than R. That's the Stanley-Reisner ring. We have, using this idea, we can describe the cohomology of the suspension of the Stanley-Reisner ring. Well, the shift in dimension, excuse me? This is the Stanley-Reisner ideal, correct. I meant to put down the Stanley-Reisner ideal, thank you. So how are we going to identify the cohomology of, well, I'm putting in a suspension, and I should have geometric realization here. I'm leaving all those terminologies out. Well, if you look at the torr, if you were to try to compute the cohomology of this part of the MAC, the moment angle complex, it simply means you look at the torr, look at the Cazul complex. There's the notion of the support. What do we mean by the support? Well, by the support, I mean there's a bunch of generators of the exterior algebra. There's a bunch of generators of the polynomial. I multiply them together. Look at all the subscripts that occur. That's the support of that monomial. And in order to get this, I would be looking at the cohomology, or the MAC cohomology. I'll put the indices in a moment, of the Cazul complex, which I'll write as an exterior algebra on these generators that are typically called UI, tensor to polynomial algebra on generators I'm calling PI, modulo the Stanley-Reisner ideal. And I want these to have support equal to, well, how many vertices do I have in, I already wrote it down, the number of vertices that is in VNR is 2 to the n. And I want the support to be every single vertex. If I look at the teeth cohomology of this thing, that is isomorphic using the identification with Tor to the 2 to the n, because that would correspond to essentially the maximal j that can occur here, minus t so to compute the cohomology of this thing, we look at the Tor, the Cazul complex, where the subscripts have to cover every coordinate from 0 to 2 to the n minus 1. It's as simple as that. So let's give some ways we can use that. Okay. Let's give an example. Oh, by the way, one of the advantages of this approach, we're allowed to use the multiplicative structure in Tor to get cycles in here. And I'd like to illustrate that with a very simple example. Question? Microphone.
So just to be clear, that's the Taylor complex on the left?
No, this is the Cazul complex.
That's the Cazul complex.
So it has exterior algebra tensor polynomial where the differential on the U is a V. And this gives me, I start with a resolution of the ground ring, which is Z, and I tensored that with the Stanley-Reiser ring. So I'm sorry, I see what you mean. I should have put here Stanley-Reisner ring. I tensored it with the Stanley-Reisner. Thank you. I'm thinking ahead to the Taylor complex and I got confused. So thank you very much. Okay. So let me do an example to illustrate how this works. I think I will leave that up there. I'm going to illustrate a simple example, one of the few that I truly understand, r plus 1 comma r. I'm going to tell you how to understand that by looking at the certain full subcomplexes there. So in order to tell you what we look at, I want to introduce a simple notation. If I have a number a, where a is between 0 and 2 to the n minus 1, and it has binary numbers, then a bar, and I'll use the word antipodal because it is the antipodal, will be replacing each epsilon with thinking of these numbers in Z mod 2, I replace 0 with 1 and 1 with 0 is all I've done, okay? So I'm adding 1 in the Z mod 2. So the antipodal of 0 is 1, 1. That's why it's the antipodal. The antipodal of 0, 1 is 1, 0. And I'm going to build up some full subcomplexes using these A's. So again, I'm looking in this case, I could take I equal to, for an A belonging to Qn, I could take I to be the 2 tuple. Take those 2 points, it's a 0 sphere. The suspension of the 0 sphere, why suspension? Because when you use the identification through Hochster, you end up with a suspension. It's a circle. So what is for this I've got 2 points, and I can write down a generator in the Cazul complex very easily. where I'm thinking of X as the polynomial algebra, but living in the Stanley-Reisner ring, and UA is the corresponding exterior. Why is this a cycle? When I take its differential, and again, I hope I'm doing this in this detail because simplicity at this hour is a good idea. I get that. But what is the Hamming distance between A and A bar? It's equal to the number of coordinates. Well, it would be R plus 1, but the scale is R. So this is 0. This is 0 in the Stanley-Reisner ring. And hence we get a cycle. This is as simple as that. So I'm going to call this class alpha of A. The A, don't forget, is the subscript of the U, and the A bar occurs in front of the X. Well, don't forget, I'm really interested in the cohomology of VR R plus 1 comma R. I'm going to define alpha to be alpha 1 times alpha 2, alpha 2 to the R, I guess minus 1. I take the product of those generators. This product is taking place in the product and the Tor. This, by the way, is a tool. These algebraic tools are not available to the authors. They don't use this technology, so they don't have this product. But this gives me a class It gives me a class in here which can be identified as a cross polytope. I don't have time to go into details. Most of you know that completely. Yes? Alpha sub A is any number in Qn. So I'm taking the alpha for the number, oh, maybe I should start with 0. I'm sorry. I'm picking particular elements in Qn. The number 0, the number 1. So this alpha 0, for example, is U0 x 2 to the R plus 1 minus 1. This is the antipodal of that. So alpha 0 denotes that class in the causal for K sub that subscript. That's the notation. Alpha, this should be alpha 1. Alpha 1 is corresponding. It will be U1 times x over 2 to the R plus 1 minus 2, and so on. Yeah, I identified it with the binary numbers. So I'm sorry I didn't emphasize that, but A could be thought of as a binary number between 0 and 2 to the n minus 1, and makes the subscript notation convenient. So does that answer the question? So I got a class. So it's a very convenient way of producing cycles, but the technical term, it's a bitch to prove they're non-trivial. So I'd like to discuss what happens next. I'm sorry about the notation not being clear. That was my fault. Okay, let me get rid of this. So what I'm going to do next is describe classes in H upper 2 to the R, suspension of by the way, the cohomology all has coefficient Z because I just don't want to write anything down. So we're going to find quite a few classes in the 2-arth cohomology of V and R. So before I go on, I want to point out that conjecture, if you remember that conjecture from a century ago, the conjecture was that there was always a class in dimension 2 to the R minus 1. I have a suspension there. So that's consistent with part of the conjecture. Almost everything else about the conjecture is wrong. but we are going to show that that group is non-zero. And I'm going to try to do it in a geometric, algebraic way and reproduce a proof, or at least a theorem, of Adams and Verk. I didn't put their reference up there, which have very, very interesting calculations in the cohomology of these guys. And we're going to do that by embedding a QR plus 1 comma R into, embedding a Vietoris-Rips R plus 1 comma R into an R. And what would you do if you wanted to do? I think the best thing to do is draw a picture. This thing has n coordinates. This thing is built out of R plus 1 coordinates. Pick R plus 1 coordinates within that list. Oh, I think we should do that in blue. I'll pick a coordinate here, and here, and so on. How many coordinates could I pick? How many selections could I make there? Well, there are n coordinates here. I want to find R plus 1. There are n choose R plus 1 choices I can make of where I am going to essentially embed the zeros and ones that are in R plus 1. Those zeros and ones, there's R plus 1 zeros and ones. I'm just going to stick them in this choice. Well, I've got a whole bunch of coordinates left over. I have a bunch of coordinates left over, which are, for example, let's say the first one that I did not choose. What I'm going to do there is fix a binary number. I'm going to fix zeros and ones in those locations. Just fix it throughout the entire argument. I'll put, let's say, a 1 here. I'll put a 0 there. Fix it. How many choices do I have there? There are n minus R plus 1 positions, and I have 2 choices for each. I have those many choices for what I could do to the remaining coordinates. And that gives me a total of, it's a funny way to multiply, this number times that number, choices of how I'm going to embed this guy in here. So that gives me n choose R plus 1 times 2 to the n minus R plus 1, different ways of embedding a sphere, a particular triangulation of a sphere, of dimension 2 to the R. I mean, we get the suspension when we do this with Cazul. And then the question is, are they linearly independent? We can use Cazul technology to prove they're all linearly independent. Adams and Verk use more combinatorial techniques. We, in fact, can get a little better using the Cazul, but I just want to give this because this is a very easy picture. Suitable choices of the embeddings give me this many, at least this many, linearly independent z's sitting in dimension 2 to the R. It's actually much bigger than that in general. There are methods we have for getting a few more. There's no general method for seeing the whole story. So that's how we get classes that are non-zero. But I like to get classes that are zero. I want to prove something about connectivity and co-connectivity. And I think the timing will work out perfectly for this. So the connectivity, we're actually not going to use the moment angle technology. We're going to use more graph theory. We will get a result which is dramatic counterexamples to the connectivity R plus 1. But we'll be able to use that technique to get co-connectivity when we apply it to the Taylor complex, which does use the Tor representation. Okay, and any questions on this so far? So given a graph, Let me look, I need some references here. Okay. Given a graph, there is something called the Laplacian of the graph. And it is a matrix. And many of you know this much better than I, so I'm just an intro, but of some of you, I'm just boring you. But in any case, it is a matrix. Lii Okay, so I'm labeling the vertices of the graph, the numbers from 0 to m minus 1 or whatever. So when I say the ith vertex, hopefully that's not confusing. I have an ordering here. And the degree of a vertex, I look at a vertex and spraying down are all the edges coming out of that vertex. That number is the degree of the vertex. And I make that the diagonal of the graph. If I does not equal j, then Lij of g is equal to minus 1 if ij is an edge, and 0 if ij is not an edge. That's the Laplacian matrix. Why are we interested in that? Oh, well, I'll tell you why we're interested, but I need some more terminology before I can tell you why I'm actually interested. Again, for general graphs, for a general graph, the complement of the graph has the vertex set equal to the original vertex set, and the edges of the graph, E is an edge of the graph precisely when E is not an edge of the original graph. It's cleverly called the complementary graph. If I take the clique complex of this complementary graph, that's often written as I of G, and I think the terminology is the independence graph, independence complex. So these are some terms we need in order to state a theorem, which is actually very powerful. And by the way, there are entire industries studying the Laplacian of a graph. And this is a theorem of well, I can't read my writing. Barone, I'll say that. I'm sure that's wrong. Berger and Mechelin. He seems to be the person who's been making the biggest contributions here. And to do that, I define lambda to be the maximum eigenvalue of the Laplacian graph of G. Then the connectivity of the independence complex of G is greater than or equal to n divided by lambda. N in this context is the number of vertices. It has nothing to do with an n I wrote on the blackboard before. And you have to correct it by a 2. I'd rather not explain why that's the case. Of course, the computing eigenvalues can be a difficult problem, but there is an estimate for the largest eigenvalue. Lambda is always less than or equal to, I think it's 2 delta. I better get that right. 2 delta. When delta is the max of the di. That's the maximum, that's the degree of the graph. We can use the main observation we have for this step is that we can use these estimates to get very strong connectivity conditions for the graph. Now, how do we do that? Well, we're interested in this graph I call G and R. The clique complex of that is our Vietoris-Rips complex. So the complementary graph has the same vertex set. Well, there were 2 to the n vertices, but there is an edge in here. A, B belongs to the edges of the complementary graph if and only if the Hamming distance between A and B is greater than R. It's easy in this case to be able to write it. And by doing some rather simple calculations, notice the independence graph of GC and R is what we are interested in. So we have to go to the complement to get to where we're after. And here's what we get. Here's N, R, and here's the connectivity. Now I'm going to lie a little bit. I'll say by this theorem, but I'm going to add some more words to that in a moment. So for 7 and R equal to 5, we get 6. Oops, R equal to 5. Already a contradiction to the conjecture. But I'll make a few others. Here's, if I take 20, 16, I get 387, which is rumored to be bigger than 17. But if we take 20 and 18, we get 24,964, which is somewhat larger than 17. One comment. As I said, it is very hard, especially with my computer technology, it is very, very hard to find eigenvalues. And I'd love to discuss any people who know technology for finding eigenvalues of the Laplacian. Related graphs have recently been, there's the new theorem called the sensitivity conjecture just proven, and the technology that is used for that may help us get information. So these numbers come about by using this estimate, which, by the way, was an estimate Yellen and I first used because it shows up when we use something called the total domination of a graph. But using the eigenvalues, we can improve it. And I did run a computer calculation. And using the eigenvalue, the biggest eigenvalue, this could be increased to 8, for example. So there's a whole world of improvements there. But what I want to do in the remaining time is go over to co-connectivity. Now, I'm just going to say some words. Our technique is to identify the cohomology of the Vietoris-Rips as a Tor. And everything I've done so far, in fact, I haven't done very much so far, but we've analyzed the cohomology from the resolution of K, or Z in our case. But now we're going to resolve the Stanley-Reisner ring and tensor that with K, giving us another approach. The standard or a standard resolution for that is called the Taylor complex. I don't have time to describe it. It's a beautiful complex, but I am going to show you what comes out of it. So I'm going to define a simplicial complex for you. Let's see, I think I wrote it down here somewhere. Here is a simplicial complex. We first start with a graph. I've used the letter G for graphs. H now will stand for a graph. NR. It has a vertex set. There are labels. They're labeled by E, A, B. These are the labels. The A and the B belong to the hypercube. And the condition on AB is that the Hamming distance of AB is greater than or equal to R plus 1 and less than or equal to N minus 1. So all I am doing here is looking at the complementary graph. And for every edge in the complementary graph, I'm taking a vertex, except for the edges that correspond to Hamming distance N. So look at all the edges in the complementary graph, except for those that have Hamming distance N, and make them a vertex. What are the edges? EAB, ECD is an edge if and only if, I'll say it in words first, in the list A, B, C, D, we do not see an antipodal pair. There's no pair with Hamming distance N and N minus 1. The way I like to write it, because this is the way you would write it in the Taylor complex, XA. These are the monomials corresponding to these generators. Is not divisible by XT, XT bar. That's the way it shows up. So this is a nice simplicial complex, and the theorem is oops, where did I write it? I want to get it right. Here it is. Is the theorem. The T minus first cohomology of VR and R is a direct summand of this is the clique complex of that graph with the shift. The cohomology we were interested in is the direct summand of the cohomology of the simplicial complex.
Sorry, Martin, what's T here?
Excuse me?
What's T? There's a T on the right and a T on the left, and I think it's not the same T.
This T, the T minus first cohomology of this is a direct summand of the 2n minus 1 minus T minus first cohomology of that.
And on the left, that's a different T, right? Just for
And this is the clique complex of this graph. I'm sorry, again, my handwriting, but thank you for making me honest. So, okay, so what's the point of this? You know, I mean, one might say, why not look at the Alexander dual? That gives me a way of turning things upside down. But this is a flag complex. Alexander dual in general is not. I could imply the technology I just described, namely the Laplacian matrix, to get bounds on the connectivity of this, which dualize the connectivity of that. Now, the best results that exist are due to Kleinemann. And let me give you a comparison between Kleinemann's results and ours. Again, using this complex. I just wrote a few out. And the numbers will be large. But again, don't forget, we're looking at 2 to the n. My God, numbers get big in this. So for VR 1210, Kleinemann says this is 1,586 co-connected. That means above that number, the cohomology is 0. We get 1,513. So we get a slight improvement. And I should mention, We have non-zero classes in degree 2 to the r or 2 to the r minus 1. That's 1024 in this case. So we know there's non-zero cohomology here. We know absolutely nothing from here to here. This is our result. And we've improved on this that much. But I like this example. VR 30, 28. Kleineman gives, bear with me, 459 million co-connectivity, 312, 152. Numbers you don't often see in a lecture on polyhedral products. We give 400 million, 360,000. So we improve, I always wanted to say is we improve on the best previous result by 59 million. However, we're still far away from the 2 to the r, which is 268 million, 475, 456. So the main point is there's some technology from graph theory, et cetera, giving us improvements. But our knowledge of what these things look like, especially for large R, is zilch. This is the best we can do at this point. I also should point out, I think this is an interesting simplicity. It's easy to describe. I could go to somebody on the street and describe it to them. They might give me money thinking I'm homeless as a consequence, but I can still tell it to them. It must have a way of analyzing it. Everything is there. It's so simple. It's surprisingly difficult. But any progress in understanding the cohomology of this clique complex gives upper bounds on the rank of the cohomology of the Vietoris-Rips, because this is a direct sum end of that. But I can't say very much more than that with the time. I actually did it within the 45 minutes. Thank you.